All right, so let's start the problem solving session for chapter 15. Okay. All right, so the question 1. So it tells us what we are given. So it tells us that we have 2500 joule of heat is added to the system. So heat is given here, and then work done is also given. And it asks us to find what is the change in internal energy. Okay, so it looks like not that difficult. It's basically the application of the first law of thermodynamics, and the first law of thermodynamics tells us that delta U is equal to Q minus W. Okay, and remember that Q is positive when heat enters the system and negative when heat leaves the system. So it looks like it is positive. So Q equal to positive 2500 joule, and this is work done on the system. So work done is negative here. Okay, it's because it is on the system. Okay. So now if I plug the values correctly with the correct sign, we can determine what is the change in internal energy. Okay. So this negative sign is very important. Okay. So negative sign because this work is done on the system. So the change in internal energy is this. Okay. All right. Number 2. Okay. So an ideal gas is slowly compressed at a constant pressure two atmosphere from 10 liter to 2 liter. Okay, so the pressure is at constant 2 atmospheric pressure, and the volume change from 10 liter to 2 liter. Okay, and this is shown in here, this line, isobaric. Okay, this process is represented in the, okay, in this process some heat flows out of the gas and the temperature drop. Heat is then added. So heat is then added to the gas, holding the volume constant, and the pressure and temperature are allowed to rise, line DA. So here pressure and temperature are allowed to rise until the temperature reaches its original temperature TA. Okay, we have to calculate for BDA process. I mean BD to A, we have to process the total work done and then the total heat flow into the system. Okay, so first we have to calculate the work done. Okay, and if you remember from the theory, the work done is the area under the graph. Okay, for we have to calculate work done for B, D, A processes. Okay, and because here we have two processes, we can write this as BD plus DA. Okay, and DA is a constant volume process. That means the work done for isovolumetric or the constant volume process is equal to 0. So the BDA is equal to WBD. Sorry, BD. Okay, and that means we have to determine the area of this rectangle. Okay, so area of this rectangle is, okay, so from here to here, this is 2 atmospheric pressure, and from here to here, this is 10 minus 2 is 8 liter. Okay, so 2 atmospheric pressure and then 8 liter. Now, you know that atmospheric pressure and liter both are not in the standard international unit. So you have to convert them into standard international unit. And 1 atmospheric pressure means 1.013 times 10 to the power 5 Newton per meter square. And then 8 liter means 10 to the power minus 3 meter cube. Okay. Oh, so here, yeah, so I did a mistake here. So let me correct it. Okay, so here it is final volume is 2 liter minus initial volume is 10 liter. Okay, so the change in volume is negative 8 liter. Okay, so that's why we should have a negative sign here, because let me use another color to make it different. So because this is equal to negative 8 liter. Okay, negative 8 liter. So that's why you have a negative sign here. So now if you multiply all these numbers, you should get something like this: negative 1.62 times 10 to the power 3, and unit for work done is a joule. Okay, so yeah, this negative sign is important for the next one. Okay, so that means work is done on the system. Okay, yeah, so work is done on the system because here you see that an ideal gas is slowly compressed. So when it is slowly compressed, okay, that means work is done on the system. Okay, and the negative sign also tells us about that. Okay, now let's try to understand what is the heat flow into the gas. Okay, so heat flow, and to do that we need this equation, the first law of thermodynamics. Okay, now here in this process BDA, in BDA, TA equal to TB. Okay, and this means there is no change in temperature. That means delta T is equal to 0. When delta T is equal to 0, the change in internal energy is also equal to 0. So when you plug this value here, you get Q equal to W. Okay, so the heat flows is equal to this 1.62 times 10 to the power 3 joule. Okay, so that means heat leaves the system. Negative sign means heat leaves the system. Okay, all right. Number 3. So what we are given here, so 0.25 mole of an ideal monoatomic gas in a cylinder expands rapidly and adiabatically. Okay, so adiabatic means um, Q equal to 0. Okay, so that's important information. Okay, and in the process temperature drops from these to these, and we have to calculate the work done. Okay, how much work does the gas do? Okay, all right. So to calculate the work done, we basically need to use the first law of thermodynamics. Okay, and first law of thermodynamics tells us that delta U is equal to Q minus W. So we basically going to determine W. And adiabatic process means Q equal to 0. So this is equal to 0. So delta U is equal to negative W. So W is basically equal to delta U. So if we can determine what is the change in internal energy, we can immediately say what is the work done. Okay. So now let's calculate the change in internal energy. Okay. Okay. So for a monoatomic gas, remember that the internal energy, the internal energy was 3/2 nRT. So delta U should be then, the change in internal energy would be this. Okay. So 3/2, and this is 0.25 mole. The universal gas constant is 8.314 joule mole per Kelvin. And then delta T, the final temperature minus initial temperature, right? Final temperature is 400 Kelvin minus 1150 Kelvin. Okay, so the direction is important. Delta T means final temperature minus initial temperature. Okay, and final here is 400 Kelvin and initial is 1150 Kelvin. Okay, so what we get is this negative 2338 joule. Okay, so the change in internal energy is negative 2338 joule. Now if I plug this value here, I get positive 2338 joule. Okay, so make sure you use the correct sign. Okay, sign is very important. So here the sign is basically coming from delta T. Okay, and delta T means the final temperature minus initial temperature. Okay, all right. Next one. Now we have to calculate the change in internal energy. Okay, so determine the change in internal energy given 1 liter of water whose mass is 1 kilogram at 100 degrees Celsius when it is fully boiled from liquid to gas. Okay, and the final volume is this. Okay, all right, and assuming the process is done at atmospheric pressure. Okay, again, the change in internal energy can be determined from the first law of thermodynamics, and that means delta U equal to Q minus W. Okay, now what is Q? Okay, so Q here is basically the heat required to change the phase of 1 kilogram of water from liquid state to gaseous state at 100 degrees Celsius. And the equation for that is this, right? During phase change, the heat required to change the phase of m kilogram of an object is basically Q equal to m times the latent heat. So here, because it is going from liquid to gas, we have to use the latent heat of vaporization for water. Okay, so it is 1 kilogram, and then latent heat of vaporization for water is this. Okay, and this is equal to 2260 times 10 to the power 3 joule. Okay, so all right, so we get the heat required. Now we have to calculate W to determine delta U. Okay, so and W is P delta V, right? The pressure times delta V. And here pressure means 1 atmospheric pressure. The question already say that the process occurs at atmospheric pressure. That means this. And delta V is final volume is this liter minus 1 liter. Okay, so the final volume means the volume of the gas is 1671 liter, and the initial volume was the volume of the water, and that was 1 liter. Okay, so it is basically 1 atmospheric means 1.1013 times 10 to the power 5 Newton per meter square. Okay, and then 1670 liter, but I want to convert it into meter cube. So, and meter cube means 10 to the power minus 3 meter cube. Okay, so when you multiply these two, you get this number 1.70 times 10 to the power 5 joule. Okay, so delta U will be then Q is 2. So let me write in 2.26 times 10 to the power 126 joule minus 1.70 times 10 to the power 5 joule is the work done. Okay. So it will be 2.09 times 10 to the power 6 joule. Okay, something like this. Yes. Okay, so this is the change in internal energy. All right. Number 5. How much energy is transferred in 24 hours? Okay, a 65 kilogram person who spends 8 hours sleeping, 1 hour at moderate physical labor, 4 hours in light activity, and 11 hours working at a desk or relaxing. Okay, now we need the metabolic rate table. Okay, so use the table and find the metabolic rate for each category, and then you can find what is the energy. Okay, so for example, for sleeping it needs 70 watt. 70 watt means 70 joule per second. Okay, so 8 hour means this 3600 second, right? So this is 8 hour in second, and the metabolic rate table tells us that for sleeping we need this much energy per second. Okay, so that's for the sleeping, and then 1 hour means just 3600 second, and then for moderate physical activity needs 460 joule per second. Okay, plus 4 hour light activity. So 4 hour means 4 times 3600 second, and light activity means 230 watt means 230 joule per second, and then 11 hour rest. 11 hour means this much second, and for relaxing we need about 115 watt or 115 joule per second. Okay, so this much energy we basically need. Okay, So if you plug all these values in your calculator correctly, you should get something like this. Okay. So this mass energy 65 kilogram person needs in one day. Okay, if that person does like 8 hours sleeping, 1 hour moderate physical labor, 4 hour light activity, and 11 hour relaxing. Okay. All right. Now we are doing some efficiency calculation. Okay, so it says that an automobile engine has an efficiency of 20%. Okay, and this is the mechanical energy, 23,000 joule of mechanical energy or mechanical work per second during the operation. Okay, first thing we have to calculate is how much heat input is required and how much heat is discharged per second. Okay, all right. So the definition of efficiency for a heat engine or automobile engine is basically a heat engine, and it is this: work done divided by QH. QH is the heat input. Okay, so heat input we have to calculate. So heat input is equal to W over E. Okay, so W is 23,000 joule, and E is 20%. Okay, and 20% is equal to 0.20. So if you plug this value here, you should get something like this: 1.15 times 10 to the power 5 joule. Okay, okay, then it asks in B, it asks us to find QL. So for a heat engine, QL is equal to these, right? So QH is 1.15 times 10 to the power 5 joule, and W is 23,000 joule. So this gives us 92,000 joule. Okay, so yeah. All right. So here a steam engine, again it is a heat engine, operates between this and this temperature. So these are the operating temperature, means the higher temperature is for hot temperature, high temperature reservoir. Low temperature means 270 degree means the low temperature reservoir's temperature. Okay, we have to find the maximum possible efficiency. Okay, so when temperature are given, we are basically trying to calculate the ideal efficiency or the theoretical efficiency. Okay, and theoretical efficiency or ideal efficiency is this for a heat engine: 1 minus TL over TH. Okay, and this TL and TH are the temperature in Kelvin scale. So here the temperature given in degree Celsius. So we have to convert them into Kelvin scale. And how to do that? We have to just add 273. Okay, so for example, this is this Kelvin, and then high temperature means this Kelvin. Okay, so if you plug this value in your calculator correctly, it should give you something like this, and 0.30 means 30%. Okay, so the ideal efficiency for this steam engine is 30%. Okay, number 8. Okay, so a manufacturer claimed that a heat input per second is okay, Heat input per second is this at 430K, and output is this at this K. And now the question is whether we believe this person's claim or not. Okay, so what it asks us to find is efficiency and ideal efficiency. Okay, so the efficiency is 1 minus QL over QH. Okay, and here QL is 4 kilojoule, and heat input is 9 kilojoule. Okay, so here input and output, by input and output we mean the temperature and the heat in the high temperature reservoir, and temperature and the heat on the low temperature reservoir. Okay, so this gives us that the efficiency, the actual efficiency, is equal to 0.56 or 56%. Okay, so this is the actual efficiency. And now ideal efficiency is 1 minus TL over TH. Okay, and TL is 285 Kelvin. So here it is already in Kelvin, so you don't need to convert it. And TH is this Kelvin. Okay, and if you do this calculation in your calculator, it gives you something like this, or 34%. Okay, now remember that in theory class we learned that ideal temperature is always higher than the actual temperature, actual efficiency. Ideal efficiency is always higher than actual efficiency. Normally the actual efficiency is 60 to 80% of the ideal efficiency. Since the ideal efficiency is 34%, the actual efficiency can never be higher than 34%. It is always less than 34%. So this person is telling lie. Okay, so we don't believe this claim. Okay, so we do not believe. Okay, all right. All right, now it's about a freezer. Okay, freezer's COP is given. Okay, COP is 2.8, and the power is given. Okay, 200 watts of power. Now here we have to calculate the time. Okay, okay, so we have to calculate the time to take to freeze an ice cube tray that contains 600 grams of water at 0 degrees Celsius. So 600 grams of ice, I mean, how long it takes to freeze a 600 gram of water to freeze at 0 degrees Celsius. Okay, so we have to basically calculate time. Okay, all right. So here you know that power is equal to W over T. Okay, so in physics 1 you learn that the power is equal to work done over T. So T is therefore W over P. So P is given, right? P is given. Now we have to basically calculate work done, right? So if we can determine the work done, then we can substitute the work done here and then find T. Okay, so how we can determine work done? Okay, so to do that, let's use the equation of COP for freezer. Okay, COP for freezer is this, right? So W is equal to QL over COP. Now COP is given, but QL is not given directly. So we have to calculate QL. Okay. Now what is the QL? QL is the amount of heat that requires to freeze 600 gram of water at 0°C. That means the heat energy is required to change the phase from water to ice. Okay, and that's very simple. This is the equation. Okay, mass and the latent heat of fusion. So what is the mass? Mass is 600 gram, and 600 gram means yeah, this much kilogram. Okay, and latent heat of fusion is this 333 times 10 to the power 3 joule per kg. Okay, so this gives us 2 times 10 to the power 5 joule. Okay, so we know QL. So let's plug these values here. Okay, so let's plug the value of W here, expression for W here. It will be QL and then P COP. So QL is 2 times 10 to the power 5 joule. P is 200 watts. And then COP is 2.8. Okay, so all together, it gives me something like this, 357 second. So it needs 357 second, and which is very close to 6 minutes. Okay. All right. The last one is about heat pump. Okay. The heat pump's coefficient of performance is given. So heat pump, the coefficient performance is 3, and it is rated to do work at 1500 watts. Okay. Okay, so work done is given 1500. Okay, 1500 watt means it works 1500 joule per second. Okay, the first thing is how much heat can it add to a room per second. Okay, so that is the first question, how much heat it can add. And then if you turn around and make it a air conditioner, okay, what would you expect the coefficient of performance? Okay, so number one, the first we have to calculate the QH. Okay, and you can calculate it from the COP for heat pump. COP for heat pump is this one, QH over W. Okay, so QH is equal to W times COP. W is given 1500 joule. Okay, and COP is given 3. Okay, so it tells us that the QH, the heat pump, can add 4500 joule energy, 4500 joule of heat per second. Okay, so I mean here watt means joule per second. Okay, and number B, COP for a air conditioner is this, QL over W. Okay, now QL is always this QH minus W. Okay, no matter whether it is a heat pump or a refrigerator or a heat engine, it is always something like this. Okay, so QH is 4500 joule, work done is 1500 joule. And then work done is 1500 joule. Okay, so this is equal to 3000 joule over 1500 joule, and that is equal to 2. So when you turn around and make the heat pump as a air conditioner, the COP becomes 2. Okay, all right, so that's it, I think, for this chapter. In the next class, I'm going to start a new chapter, okay, and a new chapter and new concept. So next class will be about static electricity. Okay, all right.